I want to show you the most beautiful proof I know. It begins with this ridge. You have met it before, even if nobody ever named it for you. It is the shape exam results fall into: heights, weights, the errors in almost every measurement anybody has ever taken. Gather up enough of anything random, and this is the hill it builds. There is a solid amount of space underneath it. You can see it. It obviously has a size. Mathematics cannot tell you what that size is, not because it is difficult. There is a proof that the formula does not exist. You could hunt for it your entire life and never find it because it was never there to be found, and yet I can tell you that area exactly. It is the square root of pi. Yes, the circle number. And there is not a circle anywhere in this problem. What we are measuring is a flat hill sitting on a straight line, so one of those two things has to be wrong. Either the area cannot be computed, or it is the square root of pi. They are both true, and getting from one to the other takes about 4 minutes and nothing you did not meet at school. Let me make the wall concrete first, because if you do not believe the wall, you will not enjoy watching it fall over. When you learn to integrate, what you actually learn is how to run differentiation backwards. The derivative of x cubed over 3 is x squared. So the integral of x squared is x cubed over 3. Every integral anybody does at school works like that. You look at the thing in front of you, you recognize which derivative it came from, and you write the answer down. Now try that with our curve. Its formula is e to the minus x squared. You square the input, you flip the sign, you raise e to that power. That is the entire shape, and it looks harmless. But when you reach for the derivative it came from, there is nothing there to take hold of. Every method you own slides straight off it. For a long time, people assumed that simply meant nobody clever enough had come along yet. Then, in the 1830s, Joseph Liouville settled the question. He proved that the functions you can build out of the ordinary ingredients, combined in any finite way at all, do not contain an answer. The thing everyone was searching for was never hiding. It is absent. So mathematicians did what they always do when something they need does not exist. They named it anyway. That is where the error function comes from, the ERF you may have run into in statistics. It is not a formula. It is a label stuck onto the area under this curve, invented precisely because there was no formula to write down. You can still get numbers out of it. Chop the region into thin strips, add them up, and the area settles down to 1.7724 and onwards forever. But that decimal never closes into anything you could write on a single line, which raises a fair question, and people always ask it at about this point. Where did this curve come from in the first place? Nobody sat down and designed it. Abraham de Moivre walked into it in 1733 while working on a gambling problem. If you toss a coin a great many times, how likely is each possible number of heads? That gives you a jagged staircase of possibilities, 1 bar for each outcome. He pushed the staircase to larger and larger numbers of tosses, and as the bars got thinner, it settled into a single smooth shape. This shape. It has kept turning up ever since, because almost anything built out of many small independent effects ends up here, whatever those effects happen to be. Before we knock the wall down, I want you to see why anybody should care, because this is not a curiosity. Every time the bell curve gets used for anything real, that number is doing work. A probability distribution has to be honest about one thing above all. The total probability of everything that could possibly happen has to come to 1. Exactly 1. So if the raw curve encloses an area of root pi, and you need the whole thing to enclose an area of 1, then you have to divide by root pi. That factor is the thing that turns a nice shape into an actual probability, which means root pi is quietly present every time somebody computes a standard deviation, every time a poll reports a margin of error, every time a factory sets a tolerance, or a physicist fits a peak, or a machine learning model assumes its errors are normal. It sits in the heat equation. It sits in quantum mechanics, where the lowest energy state of a vibrating system has exactly this shape. It sits in the Fourier transform, where this curve is one of the very few shapes that turns into a copy of itself. That is an enormous amount of weight, resting on a number that cannot be derived by ordinary means. So, here is the proof. This is the part I would keep if I had to throw away everything else. The first time I followed it all the way through, I laughed out loud, because it feels like getting away with something. We want one number, the area under the curve across the whole line. Let us give it a name and call it capital I. We cannot compute I, so we are going to stop trying and compute I squared instead. I know exactly how that sounds. We could not manage the thing itself, so the plan is to attempt something worse. But watch what happens, because this is where the wall develops its first crack. I squared just means I multiplied by itself. Two identical copies of the same integral, sitting side by side, and now a very small, entirely legal move. In the second copy, the letter we are integrating over is a dummy. It is a placeholder. Its name has no effect on the answer whatsoever, so let us rename it. In the first copy, we keep x. In the second, we write y. Mathematically, nothing at all has happened. But look at what we are holding now. An integral running along an x-axis, multiplied by an integral running along a y-axis. Two separate lines at right angles to one another. And when you multiply two integrals over independent variables like that, you are allowed to fold them together into a single integral over both at once. A double integral, sweeping across an entire flat plane. We started with a problem on a line. We now have a problem on a surface. And notice how we got here. We did not find a cleverer technique. We made the problem bigger. Now look at what is sitting inside the integral. From the first copy, we brought e to the minus x squared. From the second, e to the minus y squared. They are multiplied together. And when you multiply two powers of e, the exponents add. So the two of them collapse into a single thing. E to the minus x squared plus y squared. Stop on that exponent for a moment. X squared plus y squared. If that rings a bell, it should. It is the oldest formula in geometry. It is Pythagoras. It is the square of the distance from the origin out to the point xy. It is the equation of a circle. I find this genuinely startling every single time. We set out to measure the area under a flat hill sitting on a line. We doubled the problem, purely as an act of desperation, and a circle walked into the exponent entirely on its own. Nobody put it there. Nobody was thinking about circles. It is a consequence of the shape of the function, and it only became visible once we gave the problem a second dimension to live in. That is the pi we were promised at the start. It has been sitting inside e to the minus x squared the whole time, and one dimension was simply too narrow to see it in. Picture what we are looking at now. The flat curve has lifted into a surface. A perfect round hill standing over the plane, tallest above the origin, falling away in every direction at once. The volume underneath that hill is exactly I squared, the number we are chasing, and that hill does not care about x or y in the slightest. It cares about one thing only, how far you are from the center. Spin it, and it looks identical from every angle, which tells us that we have been speaking the wrong language this whole time. X and Y describe the plane using a grid of little squares, like city blocks. But this surface is round. Nothing about it prefers left and right over up and down. So let us describe the plane the way the surface itself wants to be described, in circles. That is the switch to polar coordinates. Instead of asking how far across and how far up a point is, we ask two different questions. How far out from the center does it sit, a distance we call r? And how far round have we swept to reach it, an angle we call theta? Every point on the plane still gets covered exactly once. We are sweeping the plane like a radar dish rather than walking it like a street map. And two good things happen at the same moment. The first one is immediate. That exponent, x squared plus y squared, is r squared, by definition. so the whole surface becomes e to the minus r squared. It depends on distance and nothing else. The second thing is the one that actually wins the proof, and it is very easy to miss. The little tile of area changes shape. In x and y, a tiny tile is a rectangle, and its area is just width times height. In polar coordinates, a tiny tile sits between two radii and two angles, so it is a small curved patch, and it gets wider the further out from the center you go. Work out its area and you get r times the change in r times the change in angle. There is an extra factor of r sitting in it. An r that was not there a moment ago, handed to us free of charge by the geometry of going round instead of going straight. Keep your eye on that r, because it is about to do the impossible. Our integral now reads like this. Sweep theta once around the full turn. For each angle, run r from the center out to infinity, and add up e to the minus r squared, multiplied by that gift, r, and the radius part, the one with the extra r in it, we can absolutely do. Because the r sitting there is exactly the leftover that the chain rule has been asking for. Let u be r squared. Then a small change in u is 2r times a small change in r. The r we needed is already present, already waiting. The wall that stopped us dead on the very first page is gone, and it was knocked over by a factor of r that nobody put there on purpose. It arrived as a side effect of describing a round thing in round language. Run that radius integral, and it collapses to 1/2. The entire infinite tail of the hill, from the center out to forever, adds up to 1/2, which leaves only the angle, and the angle is easy, because 1/2 does not depend on it. Sweeping a constant all the way around a circle is simply multiplication. 1/2 times 2 pi, the full turn. The 2's cancel. What is left is pi, so the volume under the round hill is pi. And the volume under the round hill was I squared, therefore I squared is pi. And I, the area under the original bell curve, the number we were told had no formula, is the square root of pi. Exactly, and in closed form, with nothing trailing off the end of it, that is the proof. And I want to name what actually happened, because it is easy to follow the algebra and miss the idea. On the line, the problem had no symmetry to exploit. There was nothing to take hold of. In the plane, the very same problem is perfectly circular, and a circular problem hands you a free factor of r the instant you describe it honestly. The difficulty never went away. We moved to a place where it was not difficult. Making the problem harder is what made it solvable. That move, lifting a stuck problem into a higher dimension so that a hidden symmetry becomes visible, runs through the whole of mathematics and physics. This is the cleanest example of it I have ever seen, and it is why I think it is the most beautiful proof there is. And once you have seen the move, you start noticing it everywhere. When Italian mathematicians first cracked the cubic equation in the 1500s, they ran into something that looked absurd. To reach 3 perfectly ordinary, perfectly real answers, the formula forced them to pass through the square root of a negative number, which everybody at the time agreed did not exist. They could not stay on the number line and still arrive at the answer. The route went off the line, out into a second dimension that nobody had asked for, and then came back. That detour is the reason complex numbers exist at all. The problem lived in one dimension. The solution refused to, or take stacking spheres. Pile cannonballs in ordinary 3-dimensional space, and you can prove which arrangement is best. Although it took roughly 400 years to do it. Go up in dimensions and it gets harder. And for most dimensions, nobody knows the answer even now. Except in dimension 8 and in dimension 24, where it has been settled completely. Those 2 dimensions happen to contain arrangements of such extraordinary symmetry that the problem more or less gives itself up. The question is no harder up there. It is easier, because the space is a better shape for it. That is our integral again, stated twice more. The difficulty in a problem is not always sitting in the problem. Sometimes it is sitting in the room you chose to solve it in. There is one more layer to our proof specifically, and it is worth having because it turns the whole thing from a clever trick into something inevitable. I have been treating the circle as a lucky accident. Square the integral, and a circle happens to fall out of the exponent. It was not luck. In 1850, the astronomer John Herschel was thinking about telescope errors. Aim at a star, mark down where it sits, and you miss slightly in two directions at once. He asked what the pattern of those misses has to look like, under two assumptions. First, that the sideways error tells you nothing about the up-down error, so the two are independent. Second, that space has no favorite direction, so turning your notepad round leaves the pattern of misses looking the same. Those two assumptions sound far too weak to pin anything down. They force the answer completely. The only shape that can satisfy both at once is e to the minus a constant times x squared. This curve, and no other. 10 years later, James Clerk Maxwell ran the same argument in 3 dimensions, for the speed of molecules in a gas, and the same curve came back again. So the bell curve is not just a shape that happens to be round. It is the one shape that is perfectly round and perfectly independent at the same time, which means the circle was never hiding inside it by chance. The circle is the definition. When x squared plus y squared appeared in our exponent, we were not stumbling onto something. We were reading the curve's own defining property, straight back off the page. There is one loose end, and I do not want to leave it dangling, because it is the part that usually gets skipped. The bell curve you actually meet in statistics does not carry a root pi. It carries a root 2 pi. So where does the extra 2 come from? It comes from the width. The curve we just integrated was e to the minus x squared, the plane version, sitting at its most compact. A real distribution has a spread, a standard deviation, and the conventional way of writing it puts a 2 into the exponent, so the curve becomes e to the minus x squared over 2. That halving stretches the curve sideways, and a wider curve encloses more area. Run the identical proof on the stretched version, and everything happens exactly as before, except the substitution now leaves behind an extra factor of the square root of 2. So the area comes out as the square root of 2 pi. That is the number you divide by, and that is the 2 pi you have seen 1,000 times sitting in front of the normal distribution. That too is bookkeeping rather than mystery. It is a choice about how we prefer to write the width, made because it lets the variance come out as a clean sigma squared, instead of something dragging a half around with it. The circle is doing all of the real work. One last thing, because the name on this deserves a second look, you will usually see it called the Gaussian integral, after Carl Friedrich Gauss. And the history is a lovely mess. The curve itself belongs to de Moivre, back in 1733, as we saw at the start. Gauss published the integral in 1809 in his book on the motion of the planets, and he did not claim it for himself. He credited Laplace. Laplace had evaluated it decades earlier and returned to it again in 1812. Poisson worked on it too, and in some countries it does not carry Gauss's name at all. It goes by the Euler-Poisson integral instead. I went looking for who first ran the polar coordinate argument specifically, the one I have just shown you, and I am not going to stand here and pretend the record is clean, because it is not. Depending on which history you read, it lands on Laplace or on Poisson. 4 names, 1 integral, and a paper trail that argues with itself. So the most famous integral in all of statistics is probably named after the man with the weakest claim to it. Which is oddly fitting, because what really solved it was a circle, hiding inside a curve that appeared to have nothing whatever to do with circles, waiting for somebody to give it enough room to show itself. What I find beautiful is not the answer itself, but the fact that it was sitting there the entire time, and all anybody had to do was stop looking at it edge-on. If you want more of this, subscribe, because the next one is about a curve built out of nothing but circles. Not one circle hiding inside it, but thousands of them, spinning at once, tracing out any shape you like. That is the Fourier series. And it is today's idea, running in reverse.